So welcome back guys, and in this video we are going to learn about a very important concept which is very important because next video we are going to learn about Hall effect, and there we are going to use this expression. So important concept for Hall effect. So this is kind of a preparation video for Hall effect video. So suppose one electron is here and it has a momentum of pt, and there might be some other electrons also at momentum. So this pt is the momentum p at time t, and suppose in dt time some of the electron advances without being collided, and their momentum is p t plus dt, and some may have collided with other electrons and scattered. Some may have scattered like this. So we want to calculate, so what will be pt plus dt, that we are interested in. So how to calculate that? So earlier we have learned about the concept tau, that is the relaxation time, and generally this is the for average time for one collision. So if one collision happens in tau time, right? So in unit time, so in tau time happens one collision, then unit time it is 1 by tau, and then dt time it is dt by tau, right? So in dt time, this is the probability of probability of collisions. So like these many collisions, I mean by that these many collision will happen. So the chances that the electrons has not collided then will be not collided. So in here, so the force acting on these particles is Ft, right? So if the force acting on this particle Ft, so generally before if there is a collision or not collision before this time, the momentum gain will be in generally Pt plus Ft dt plus some higher order term. There could be some higher order terms. So this is the momentum gain from this time before the collision. Now these fractions has not collided, so their momentum we can write definitely that p dt equal to 1 minus dt by tau into pt plus ft dt plus order of dt square. So these many electrons has not collided, right? So this is the thing. Now we can also show here for the amount of for the electrons, so not collided, they are not collided. So we can also show for collision or for collided, for electrons who have collided, they actually contribute to the higher order terms, and they can usually, so we will neglect any second order term we will neglect anywhere. And for the electron who have collided, actually we know that when they collide, usually they after collision, so electron coming from each direction, they will usually grow out in various direction, and their average velocity is generally zero. So this p average is generally zero. So this term will not contribute. So these electrons only have this term will not contribute for the collided electrons. Only they will have the this term which will contribute. Only this term will be there which will contribute, because suppose you just imagine, so the electron which was in here not collided, and one electron collided just goes off in some direction. Then let's suppose in here two electron remains, one electron again collided goes up in some direction, and again let's suppose here one electron remains and one electron goes up in some direction. So if it has collided at, let's suppose this is the t time and this is the t plus dt time, so if it has collided, then it goes in random velocity and the average velocity goes down to zero. So for that electron to be reach this point, to for so suppose for that electron which have not collided, if it has reached this up to this point, then it has only this force. So this force is acting on this, and in dt time it gains only this momentum, because before that, suppose this electron before suffers a collision at this point, suffers a collision and then travels up to this point. So suffers a collision and then travels up to this point without collision, then it gains only this momentum. Only this momentum will be there, because this at this point this electron has p average to be zero, and it gains only this momentum, right? So and the fraction of electrons that has collided, we have said the dt by tau. So this dt by tau into ft dt, it is again a second order term, second order, so neglect. So this has a negligible contribution. Neglect the contribution. Neglect the contribution. So this has a negligible contribution. That's why this is so that's why it doesn't matter. So only we can consider this term, and from here we will get our expression. What will be the momentum at pt plus dt for those electrons? So this was our expression. Now let's simplify it. So this gives pt plus ft dt plus order of dt square, then minus pt tau dt minus ft dt square tau minus order of tq, anyway we neglect. And also if we now take the limit of dt tends to 0 and we divide everything by dt, dt here ft dt, so dt tends to 0, so we see that only so these terms, so dt tends to 0, so these terms will go to 0, and also this term is also going to 0, because anyway if we take dt tends to 0, so this is second order term. And so we want to calculate this term p dt plus dt minus pt and divided by dt, because we want to calculate dp dt. All right, so that will give you ft minus pt by tau, right? And these terms anyway goes to 0, because one t will be divided but another dt will be there, and dt tends to 0, so this terms goes to 0. So this is our expression for dp dt, which is nothing but pt divided by tau plus f of t. This is an external force. Okay, so these expressions we are going to use in the in deriving Hall effect, and so this is the general expression that we wanted to derive, and there is some underlying concept also about these collisions and all. I think that is clear. All right, until we meet, bye bye.